Welcome to lecture number 7 of module 1. In the previous lecture, we have introduced ourselves to how to determine different types of Atterberg limits. Having determined Atterberg limits and also understood about arriving at the grain size distribution, with the help of this data, it is possible to classify the soil. So, in this lecture, we will try to see the soil classification systems which are widely used, and then we discuss about some salient aspects with reference to the limitations of Atterberg limits and all. So, this lecture 7 is about the soil classification. So, if you look into the Atterberg limits, we have liquid limit, plastic limit and shrinkage limit. If you try to see the engineering use of liquid limits, they are often used directly in specifications for controlling soil for use in fill materials or any other application. Used for predicting also activity of the clay. The activity of the clay is defined as plasticity index over is the ratio of plasticity index or a percentage clay passing 2 micron. So, this Atterberg limits are used for predicting activity of the clay or frost susceptibility also. The plasticity index indicating the magnitude of water content range over which the soil remains plastic, and the liquidity index indicating the nearness of a natural soil to the liquid limit. If the liquidity index is close to the liquid limit, that means that it is almost in a fluid state, and are particularly useful for characteristics of the soil. So, these are used for classifying fine grained soils. Atterberg limits are very much useful for classifying fine grained soils. Further, greater the liquid limit, the greater the compressibility of the soil. Some soils exhibit very high liquid limits. For example, bentonite has got very high liquid limit, and greater the liquid limit, greater the compressibility. And liquidity and consistency indices are good indicators of the consistency of the soil. So, if you have a soil which is actually having a low consistency index, that means that if you have a consistency index of 0.4, that indicates a soft state of the soil. So, the limitations as far as the Atterberg limits are concerned, the Atterberg limits give no indication of the particle fabric or residual bonds between the particles, which may have been developed in the natural soil, but are destroyed in preparing the specimen for the determination of limits. As you all know, we do the liquid limit test on a remolded sample, which is actually passing say 0.425 mmC or 425 micron. The Atterberg limits give no indication of the particle fabric or residual bonds between particles, which may have been developed in the natural soil. So, the bonds which are actually existing in the natural soil might not have been represented in the liquid limit test, but are destroyed in preparing the specimen for the determination of limits. So, this is one of the limitations of Atterberg limit, or you can say that the limitations in determining liquid limit test. We also discussed that with the help of Atterberg limits, we can estimate or assess the activity of the soil. So, the plasticity of a given clay depend upon the nature of the clay mineral. So, the type of the clay mineral, the amount of the clay mineral present. Based on the laboratory tests for several soils, Skempton 1953 made the observation that for a given soil, the plasticity index is directly proportional to the percent clay size fraction. So, a relationship between plasticity index and percent clay size fraction present in the soil was actually presented by Skempton in 1953. So, it is defined as activity is equal to plasticity index over percentage clay fraction, where Pi is equal to plasticity index and C is the percentage clay size fraction by weight. So, activity AC, A suffix C is a function of type of clay mineral present in the soil. So activity is used as an index property to determine the swelling potential of an expansive soil. So if you know the activity, it is possible to assess the swelling capability or expansiveness of a given soil. So in this table, different activity values of minerals are given. The sodium based mantimonite can have activity values in the range of 4 to 7. Calcium mantimonite can have activity value up to 1.55. Illite has 0.5 to 1.3. Kaolinite will have low value 0.3 to 0.5. Halloysite hydrated can have 0.1 and quartz activity value is 0. So the activity value of a sand, for example, which is predominantly having quartz, can be 0. So activity value of the minerals like sodium mantimonite is very high, and when it comes to illite, it is 0.5 to 1.3, and then kaolinite 0.3 to 0.5. The clay minerals with kaolinite, a stable clay mineral, will have low activity. That's what we have discussed in the previous slide. Whereas those soils with mantimonite, known to be subject to large volume changes depending on the availability of the water, will have high activity values. So the soil classification can also be made based on the ranges of activity values. When the activity value is less than 0.75, the soil is classified as inactive as far as expansiveness is concerned. 0.75 to 1.25, it is classified as normal clay, and greater than 1.25 is classified as active clays. The same in another graphical version, which is actually shown here, the classification of the soil according to activity, where on the x-axis we have percent finer than 2 micron, that is passing 2 micron, which is actually plotted in percentage on x-axis. On the y-axis we have plasticity index. So the soils which are actually falling, having activity values here, they are actually potentially susceptible to expansive nature. And here they are actually, say, like light type of clays, they fall here, and kaolinite type of clays, they are somewhere here. In this slide, according to Seed et al. 1964, they have presented investigated about the plastic properties of several artificial blends of bentonite, kaolinite, and kaolinite, bentonite in different blends. And it is presented here with plasticity index on the y-axis and percentage clay size fraction on the x-axis. So here activity value as high as 5.4 is reported here. So according to Seed et al. 1964, the activity is defined, suggested that they have that Pi divided by percentage clay size fraction minus C dash, where C dash, which is the correction, which is given as suggested as 9. So with this, particularly the plastic properties of several artificial blends of bentonite and kaolinite yields that the relationship between activity and plasticity index and percentage clay size fraction is modified as A is equal to Pi divided by percentage clay size fraction minus C, where C dash is equal to 9. Now, coming to the soil classification systems, generally group together broad categories of the soil that have similar features or properties which are considered to be of importance. For many projects, it is required to identify the soils which are actually having identical properties or broad categories of the proper characteristics of broad characteristics. So as a result, a classification system is not necessarily an identification system in which all pertinent engineering properties of a material are determined, but however, it can work out as a guideline for selecting the material and investigating further based on the classification which has been made. So because of this, the soil classification should not be used as the sole basis for the design or construction planning. So classification systems are generally, they group together broad categories of the soils that have similar features or properties which are considered to be of importance. So the soil classification system should not be used as the sole basis for the design or construction planning. The requirements for a satisfactory engineering classification systems include limited number of groupings. So it is required so that the system is easily to remember and use. The symboling has to be simple so that the classification, the limited number of groupings, and then the system is easy to remember and use. So grouping should be on the basis of only of a few similar properties and generally similar behavioral characteristics. So if the grouping is made, the group should have soils which are actually having similar behavioral characteristics. And the properties and behavioral characteristics should have meaning for the engineering use and construction profession. That is, relate to soils handling characteristics, shear strength, volume change characteristics, and permeability. So the two important requirements which we have discussed in this slide, one is that limited number of groupings, and properties and behavioral characteristics should have meaning for the engineering use and construction profession. Thirdly, the descriptions used for each grouping should be in terms that are easily understood and are common use for indicating the soil type and its properties. As a fourth requirement, classification into any grouping should be possible on the basis of visual identification, limited to grain size distribution and Atterberg limits without special tests or equipments. So if we have the data of grain size distribution and Atterberg limits, so the classification into any grouping should be possible on the basis of the simple tests, that is particle size distribution data and Atterberg limit test data. So the fundamental idea of the soil classification system is to collect the soil samples from the field. It can be at different depths and different locations, and perform easy and inexpensive tests on soil samples, typically grain size distribution test and Atterberg limit test. Based on the results of these tests, classify the soils in question. That means that whatever the soils which are tested, they can be in the class to it helps classify the soil in question. And based on the classifications of the soil, whether or not be appropriate for the identical intended usage can be guessed. If yes, perform more extensive lab tests on soils as needed. So if the soil classified in a particular group is suited for particular application, then perform more extensive lab tests in the soils as needed. So historically, the most widely used method of classifying soils has been through visual identification and size of the soil grains. So we have different sizes, bulk particles, bulk size ranging to flaky particles to very plate shaped particles. So some of the particles cannot be seen, but visual identification will allow to some extent. Then size of the soil grains and plasticity of the soil being used as the basis for indicating the soil types. For example, if you have silt and clay, there is a possibility that sometimes it is required how to distinguish between silt and clay. This is possible with some identification methods, like which is suggested here, to distinct between silt and clay. So if you look into this plasticity, the silt will have low plasticity and clay will have high plasticity. And if the equal amount of soil which is oven dried and air dried is dispersed in a jar having water, then silt settles rapidly and the clay remains in suspension even after 24 hours. And dilutancy, that is reaction to shaking, is high for silt and low for clay. So with this is possible to distinguish between silt and clay. And the dry strength, the soil which is silty soil, the resistance to breaking is very low, and clay in the dry state, some clays where they having high plasticity characteristics, they have very high woven dried strength. So, this is a function of plasticity, colloidal fraction content of the soil, that is that which is actually having very fines which are actually more than 2 micron if it is high. And so, this is this particular distinction between silt and clay is possible with the simple methods which are actually suggested. One is by plasticity, other one is that sedimentation rate and dilutancy and dry strength. So, which is basically a function of plasticity and colloidal fraction of the soil. So, the classification of the soil can also be done by basis of the grain size. In the previous lectures, we have actually discussed that soil which is regarded as which is less than 4.75, which is actually called as sand, silt and clay, and the ones which are actually greater than 4.75 and less than 20 mm, which is called as gravel, and above that is 20 to 80 mm and then more than 80 mm as cobble. So, here the classification of soil on the basis of the grain size according to Bureau of Indian Standards 1498 is shown here, and the particle sizes which are actually indicated here, they are in millimeters. So, the clay which is less than 2 micron, that is 0.02 mm, is regarded as the size of the soil particles which are actually less than 0.002 mm is regarded as a clay, and the size of the soil particles which is less than 0.075 and greater than 2 micron or 0.002 mm is regarded as silt, and in the sand we have fine sand which is from 0.425 to 0.075 mm, medium coarse sand it is 0.425 to 2, and coarse sand as 2 to 4.75, and then we have gravel, and then we have cobble. According to unified soil classification system, which we are actually going to discuss in length. So, more or less the division is identical, where you have the particles which are actually more than 19 mm, gravel particles which can occur in the soil which are more than 19 mm, they are called bulk size particles, and the classification which is actually shown here resembles almost equivalent to the BAS 1498. And in this slide, the classification of soil on the basis of the grain size according to ASTM, the American Society for Testing and Materials, and where they classify anything greater than 4.75 as gravel, and between 0.075 mm to 4.75 mm is classified as sand, which is actually similar to the previous two classification systems of a soil on the basis of the grain size, and clay which is actually regarded as 1 micron to 5 micron, and silt which is recorded as 5 micron to 0.075. And according to British soil classification system, which is actually shown here as gravel which is actually more than 2 mm, and sand particularly here 60 micron to 2, which is actually regarded as a sand, and a silt, and then clay. So, different classification systems adopt different size limits for the soil, but any soil portion or a fraction which is passing 75 micron or 0.075 mm is called as percentage fines, which is actually having great relevance in influencing the engineering properties of the soil. So, the soil classification methods, if you look into it, there are two types of methods widely used. There are many methods, but here in this we are limited to ASTO classification system, and other one is the unified soil classification system. The soil classification is basically the arrangement of the soil into the various groups or subgroups to provide a common language to express briefly the general usage characteristics without detailed descriptions. So by knowing the particular group, it is possible to guess how the particular characteristics can be. So the soil classification aim basically is to arrive at the arrangement of the soils into various groups or subgroups to provide a common language to express or briefly to address the usage of the characteristics, general usage characteristics without detailed descriptions. So by knowing that or seeing that group, we will be able to assess the soil whether it is more permeable or whether it is more compressible or has got high compressibility characteristics or has got high plasticity characteristics, etc. So both the systems what we are going to discuss, ASTO system and unified soil classification system, they use simple index properties like grain size distribution data and liquid limit and plastic limit properties of the soil. Now let us discuss ASTO classification system, and this considers both texture, that is GSD classification system, and GSD grain size distribution data and Atterberg limits. This was originally proposed in 1919 and the system was last modified in 1945. Widely used for highway and transportation engineers, and this is performed on the part of the soil sample that falls in the gravel to clay size range. That means that it actually classifies the soils and puts the soils in different groups based on in the sizes ranging from for the gravel to clay size range. Once the group classification has been found, so here a group classification is arrived based on the properties which are actually used from the grain size distribution data and Atterberg limits data. And it is this reference index which is actually used in this particular classification system is named as group index, which is indicated as GI, and this is used to compute further classify the soils. So if you have the high value of the group index, that indicates that the particular soil has inferior characteristics. So in the ASTO classification system divides the groups into soil groups into A1A, A1B, A2, A2 to A4, A25, A26, A27, A3, A4. So A4, A5, A6, A7, 5, A7, 6 and A8. A8 is basically, so total 8 groups and then there are some subgroups within it. And here A8 is some for the soils like which are PT or mucky in nature or organic soils are put based on the visual identification. They are put in the A8 group. So the group index for the in the ASTO classification system for the groups which are actually A3 and above. That means that A3 to above can be computed by using this particular expression. GI is equal to F minus 35. F is nothing but the percentage of soil sample passing 0.075 mm sieve, that is 200 mm sieve, plus 0.005 into LL minus 40 bracket N plus 0.01 into F minus 15 into PI minus 10. So here the plasticity index was used and percentage fines was used, and so with this the group index parameter can be obtained. Similarly, for the soils in A1 to A1 or A2, the group index is given as 0.01 into F minus 15 into PI minus 10. That is only this component is defined. So generally this is the widely used, and once this is used, and suppose if you have a PI is equal to 10, then that means that this particular component will become 0. Then we have only this component. So in both the formulas, what we see is the F which is used in the percentage of the soil sample passing 200 sieve or 200 number sieve or ASTM 0.075 mm sieve. So the GI, which is nothing but a function of grain size distribution, shape and surface area. The group index, which is, so the group index is that which is depend upon the surface area. So higher the surface area, then the group index can get affected. The shape, that is shape of the soil particles, and then grain size distribution data. The ASTO classification system in GI means what we are doing is that rating of a soil as a subgrade material within its own group. As I said that this is actually developed for highway and highway constructions. So the rating of the value of the soil as a subgrade material within its own group. Higher the value of the GI, poorer is the quality of the material. That means that higher value of the GI means the soil can actually has low load carrying capacity characteristics. The useful hints in the classifying the soil, once we have the grain size distribution and Atterberg limits data, always begin on the left hand side with the A1A group. So once the chart which actually A1A group, once we eliminate A1A group, then go to A2 like that and check each of the criteria. If any criterion is not met, step to the right and repeat the process. So the chart which is actually not given, but if you have a chart, always begin on the left hand side with A1A group and check each of the criteria. If any criterion is not met, then step to the right and repeat the process. Do not begin at the middle of the chart. Suppose in order to complete the classification hurriedly, do not begin the classification in the middle of the chart. Now let us take one example problem, example 1 with the ASTO classification system, whatever we have discussed. So in this problem, the percentage passing 2 mm size of the particles, that is passing number 10 sieve is 100%. That means that all particles are actually finer than this particular 2 mm size. Percentage passing number 40 sieve, that is 0.425 mm size, is 80%, and percentage passing number 200 sieve is 58%. That is percentage fines are here 58%, that is F is equal to 58. And liquid limit is 30 and plasticity index is 10. Now the group classification based on the chart is evolved as A4. That is, from the chart, if you use from the chart data, you will get with the data whatever the limits which we have. With that, it is classified as A4. Then by using the equation which is actually given for group index, determine for F is equal to say 58 and with plasticity index is equal to 10, we will have that second component of that expression will become 0, then GI is equal to 3.45. That means that GI is equal to 3, then hence the group classification which is indicated as A4, that is obtained from the chart based on the data which is presented here, and 3 within the bracket which is indicated as 3. So this indicates that, which is classified, this interprets that this particular soil which is actually having these characteristics has got fair to poor subgrade rating. Coming to the example which is percentage passing through passing number 200, that is 95, that is passing 75 micron sieve is 95% and liquid limit is 60% and plasticity index is 40. Now having run through the chart, the group classification is obtained as A76 and determined with F is equal to 95, GI is 42. So here the 95, that is percentage finds percentage is actually taken as percentage and then computed GI is equal to 42. Now you can note this GI which is actually obtained is very high. So the group classification is indicated as A76 which is written as A75, but it is A7642. That means that this is the rating which is actually understood as poor subgrade rating, the poor subgrade rating. The limitation, if you look into this, the limitations are that the criteria for the groupings are logical, but shortcomings include requirement for a laboratory testing. In order to determine a classification and the difficulty in using the code designation and remembering the requirement for each of the designations. Somewhat these groups are difficult to remember. The criteria for the groupings are logical, but shortcomings include the requirement for a laboratory testing and in order to determine a classification and the difficulty in using the code designation. So, the code designation is mainly has difficulty in remembering, and unless we look into the interpreted results, it is not possible for us to understand about the interpretation of the behavior of the soil. Now, as I said that the second method which is discussed is the Unified Soil Classification System, that is USCS, first devised in 1942 and last modified very recently in 1991. Like the ASTO system, it also uses the both grain size distribution and Atterberg limits. What is required is that percentage sample, which is gravel size fraction, sand size fraction and silt and clay fraction, and uniformity coefficients. We have discussed that Cu is equal to D60 by D10 and coefficient of gradation Cc is equal to, that is D30 square by D60 into D10. So, once you have the data and liquid limit and plasticity index on the portion passing 0.425 mm sieve. So, once we have this data, it is possible to group the soils which are actually having the identical characteristics. So, let us see what will be the classification procedure which is adopted in the Unified Soil Classification System. So, determine the percentage finer than 200 sieve, that is 0.075 mm sieve. That is, if percentage finer passing 75 micron is less than 50%, then go to step 2. If it is greater than or equal to 50%, go through step 3. So, what is in step 2 is that the coarse fraction is nothing but 100 minus percentage passing 200 sieve. So, if F1 is the percentage passing 4 number sieve, that is 2 mm, but retained in 75 micron sieve, that is sand. So, if F1 less than R200 by 2, then the coarse fraction is more gravelly than sand. That means that if F1 is less than R200, that is which is nothing but 100 minus F200, which is actually given above, and if F1 is less than R200 by 2, then the coarse fraction is more gravelly than sand, and if F1 is greater than R200 by 2, then the coarse fraction is more sandy than gravel. The step 3 is nothing but that is actually addressed by using Casagrande's plasticity chart, and that helps us to classify the soil based on the Atterberg limit test data. So, this Unified Soil Classification System is originally proposed by Arthur Casagrande in 1942 and revised by the Corps of Engineers and US Bureau of Reclamation in 1952 and recently in 1991. Widely used by various organizations, geotechnical engineers in private consulting business and building codes. So, the Unified Soil Classification System subdivides the soil into the following heads. One is that soil is basically divided into 3 predominant types. One is coarse grained soil, other one is fine grained soil. This was discussed earlier. Then in peat type of soils, which are actually organic soils having peat or muck nature. So, they are actually subdivided separately, coarse grained and fine grained soils. And coarse grained soils are predominantly gravel and sand, and fine grained soils are silt, inorganic clays, organic silts and clays. So, we have fine grained soil which is predominantly divided into silt, inorganic clay and organic silt and clay. It is also known as Casagrande's extended classification system. So, the 2 major divisions which are there, a soil is coarse grained, gravelly or sandy, if more than the 50% is retained on a 200 mm sieve, that is on a 200 number sieve, that is 0.075 mm or 75 micron sieve. As a fine grained soil, the silt and clay, if more than 50% is passing through a 200 number sieve, that is classified as fine grained soil. So, if percentage fines is more than 50%, which is passing, then is classified as a fine grained soil. So soil is further classified by the number of subdivisions with primary and secondary characteristics. So here the following symbols are used. Gravel, which is indicated as G, and silt, which is actually indicated as M. The original origin of the name of the silt is Swedish MO, which is silt, and S for sand, and C for clay, W for well graded. That means that it actually has got various ranges of the soil particles, and P for poorly graded or gap graded, and O organic, P's T for PT type of soils or highly organic soils, and C well graded with some clay, and L which is indicated for low plasticity, I for intermediate plasticity, and H for high plasticity, F well graded with excess fines. So this F symbol, which is actually used for well graded for the excess fines, which is not generally comes in the in grouping of the soil, but what you will find is that suppose if you have got some clay with low plasticity, then it can be indicated as a CL, or say some clay which is actually having with high plasticity, it can be indicated as a SH. Or if you have a sand which is well graded in nature, then can be indicated as SW. And if the sand which is actually having same size of the soil particles or uniform size of the soil particles, then it can be indicated as SP. So the criteria of classification of the coarse grained soils into 4 groups. One is the W, well graded, Cu has to be 4 for gravels, and Cu has to be greater than 6 for sands, and Cc has to be 1, 2, 3. So here both Cu and Cc have to be satisfied, and with fines that is finer than 75 micron and less than 5%. So it is said as well graded, the fines should not be more than 5%. And the poorly graded, Cu is less than 4. That means that in the poorly graded, the slope of the grain size distribution curve is very steep. So the Cu will be less than 4 for gravels and less than 6 for sands, and Cc will be not between 1 to 3. So please note down here, in case of a poorly graded or gap graded, the Cc will not be between 1 to 3 with fines again less than 5%. And C, the plastic clay fines with the Pa greater than 7 with fines more than 12%, and M non-plastic silty fines Pa less than 4, so with fines more than 12%. So fines more than 12%, but non-plastic silty fines, and they are indicated as with M, with plasticity index less than 4. So the criteria for the soil classification of the fine grained soils, basically it is done by using the plasticity chart. So basis of the plasticity chart is that once you have got liquid limit and plasticity index, and which is actually plotted, then it is possible for you to express to classify the soil. So the experimental results from the soils tested from different parts of the world were plotted graphically of plasticity index versus liquid limit. A plasticity index on the y-axis and liquid limit on the abscissa. It was found that clays and silts and organic soils lie in distinct regions of the graph. So this particular chart was arrived based on the data which is actually collected from the number of soils like clays, silts and organic soils, and they found that it is found to distinguish this with the help of the chart. So here in this particular slide, a Casagrande's plasticity chart is shown here, and on the x-axis what you see is liquid limit, which is shown here. On the y-axis the plasticity index is plotted, and here this particular line which is called the A line, the equation of the A line is that IP is equal to 0.75 into WL minus 20. So any soil which is actually, so if it is demarcated in 3 zones, one here and one here and one here, and here this particular zone the soil actually will have low plasticity and medium plasticity, and here the soils actually have high plasticity. Any soil which is actually lies above A line is called inorganic clays of high plasticity, particularly if you are having a liquid limit more than 50, and if it is lies below the A line, then it is called inorganic silts of high compressibility, and also some organic clays are grouped here. And here in this particular zone where liquid limit greater than 30 and less than 50, and here with the plasticity index in this boundaries, where inorganic silts of medium compressibility and organic silts. For example, if you have got a soil which is actually having identical liquid limit but have different plasticity characteristics, they are actually classified differently. So, if I have one soil here and one soil here, they are actually demarcated as a different types of. So, here in this zone, particularly these are actually for the cohesionless soils or the soils which are actually possessing non-plastic or low plastic silts. So, these are actually having plasticity less than 4 or say 4 to 7, they are actually put here in this particular zone. And what we see here, the red line, which is nothing but called U line. So, any data which is actually falling in this region, that means that the test data has to be repeated, and this is actually upper bound value which is actually plotted, upper bound line. The equation for the U line is indicated as IP is equal to 0.9 into WL minus 8. So, if you have, so the mostly all the soils which are actually above this, above A line, on or above line are classified as inorganic, and below are all organic. So, you can see that these are all the some inorganic silts and low plasticity silts are placed here. The features are that the chart is divided into 6 regions, 3 above, that is A line delineates the boundaries between the clays above the line and silts and organic soils below the line, and 3 below. So, equation of the A line is 0.73 into WL minus 20, and U line defines the upper limit of the correlation between the plasticity index and liquid limit. If the results of soils fall above the U line, repeat the Atterberg tests. And the equation for the U line is given as IP is equal to 0.9 into WL minus 8. So, all points representing inorganic clays lie above A line, and all points for inorganic silts lie below A line. Points representing organic clays are usually located within the same region as those representing inorganic silts of high compressibility, and organic silts in the region assigned to inorganic silts of medium compressibility. So, in doubtful cases, liquid limit should be determined for an oven-dry specimen as well as the fresh one. If the decrease in liquid limit is say 30% or more, then the soil is classified as organic because of the loss of ignition of the organic matter. So, in the doubtful cases, the liquid limit should be determined for an oven-dry specimen as well as the fresh one without oven drying. If the decreases by liquid limit by 30% or more than, the soil may be classified as organic. Thirdly, as the liquid limit increases, the plasticity and compressibility soils also increases. So, the dry strength of the inorganic soils represented by points on lines located above A line increases from medium to samples with a liquid limit less than 30 and to very high for samples with a liquid limit greater than 100. So, let us now club the unified soil classification charts obtained from the grain size distribution data and plasticity chart, which is actually discussed in the previous slide. So, here in this a category which is actually defined, the coarse grain soils, major division is that coarse grain soils percentage passing 200 sieve less than 50, and gravels which is percentage passing 4.75 mm sieve less than 50%, and gravels with little or no fines. So, here with the Cu value greater than 4 and Cc between 1 and 3, and so gravels with this range, well graded gravels, gravel sand mixtures with the little or no fines is classified as GW. So, well graded gravel, it indicates that GW indicates the well graded gravel. Similarly, poorly graded gravels are gravel sand mixtures, little or no fines, which is actually indicated as GP. So, here the gravel which is actually having almost uniform size particles, so that is actually grouped as GP. Similarly, Atterberg limits below A line and PI less than 4. So, the silty gravels are gravels and sand silt mixers. So, if I have a silt which is actually blended with gravel, then it is actually indicated as GM. Similarly, gravels with the fines having plasticity index more than 7, Atterberg limits lie above A line, then it is indicated as GC. So here with the gravel soil, we have seen that GW, GP, GM and GC. Similarly, here for sand, similar trend we have adopted here SW, SP, SM and SC. Here this value, as I discussed earlier, it is CU value is more than 6 and CC value between 1 and 3. And for not meeting the two criteria, and here in this case poorly graded and CC value not between 1 and 3, then it is actually said as SP. So the sand with fines with appreciable amount of fines, silty sands and sand silt mixtures with plasticity index less than 4, and they are actually indicated as silty sand or sand silt mixtures with SM, and clayey sands and sand clay mixtures is indicated as SC. So here we have seen that sandy type of soils with different types of gradation, SW, SP and SM with some silt mixtures, or with the clay sands or sand clay mixtures indicated as SC, the symbol or group which is indicated as SC. And fine grained soils with the percentage passing 75 micron sieve is greater than 50%. So here according to plasticity chart, which is the criteria which is we have discussed, when inorganic silts with very fine sands and rock floor and silty or clayey or fine sands indicated as ML, and there is also a boundary soil which is actually indicated as CLML. That means that the doubtful cases where you have got a twin grouping which is called CLML grouping, and silts and clay with liquid limit less than 50%, inorganic clays, low to medium plasticity, gravelly clays and sandy clays and silty clays, lean clays, basically they are actually grouped as CL. Organic soils and organic silty clays of having low plasticity, they are grouped as OL. So here for the fine grained soils, we are actually seeing groups like ML, CL and OL. And for the silts and clays, liquid limit greater than 50, which is inorganic silt, and micaceous or diatomaceous and fine sandy and silty soils, and elastic silts which is indicated as MH, inorganic clays with high plasticity and fat clays having high compressibility and high plasticity indicated as CH. So MH and CH, organic clays with medium to high plasticity indicated as OH. So here you can see that OH, and PT or mulch and other high organic soils is indicated as PT, P and small letter T. So here according to ASTO classification system, we classify the PT type of soil as A8, and here it is indicated as PT, that is the for the highly organic soils. And classification based on the percentage of the fines. So if the percentage passing number 200 sieve, that is 75 micron sieve, is less than 5, then it is indicated as GW, GP, SW and SP, and greater than 200, it is indicated as GM, GC and SM and SC. Between 5 to 12, these are actually called as the borderline symbols. So they carry dual groups, which is nothing but if you have percentage passing greater than 5 and less than 12, then we have it can be GW GM and or GW GC or GP GM, GP SC, SW SM or SW SC and SP SM and SP and SC. So Atterberg limits above A line and plasticity index between 4 and 7 are borderline case, so it needs dual symbols. Atterberg limits above A line and plasticity index between 4 and 7 are borderline cases, and it needs dual symbols. So as I said there, that is actually on the left bottom of the plasticity chart, and which is actually indicated as CLML group. So in this particular chart, what you see on or above A line, they are actually called as inorganic clays, and below A line, they are actually classified as silt and organic soils. So the plasticity chart, which is here the equation of this is the A line and this is the U line, this is the U line what we have actually discussed. So here the horizontal for the at PI Pi is equal to 4, that is Pi is equal to 4 and liquid limit is equal to 22.5. So, any soil which is actually falling in this zone is carrying a dual symbol, that is called CLML, and the equation of the U line, that is here vertical at liquid limit is equal to 16, that is liquid limit is equal to 16, that is somewhere here, and then it actually starts here. So, this is for the the U line which is actually shown here. So, any soil which is actually falling above A line and inorganic clays, very high woven right strength and very low clay, and they have high hard at plastic limit. So, the soil which is actually falling on above A line, they exhibit high woven right strengths and very low permeability. What we see the K, which indicates that permeability, and they are actually very hard at plastic limit. And similarly, the soil characteristics which are below A line, that is in this zone, they are basically silts and organic soils, very friable because water content is close to plastic limit, and lower woven right strength. That means that they possess actually the low woven right strength. But similarly, if you see a soil which is actually having identical liquid limit, but which is actually falling in this region, can exhibit high woven right strength. So, here in this particular chart, it indicates that different samples from the same soil stratum of the same geological origin, they actually possess or they fall above A line. So, the characteristics, whatever the geological origin, they are having identical characteristics. So, they actually fall, and then which of the same soil stratum, and they actually fall here. So, here what is actually, it shows that the compressibility increases, the permeability of the soil will be very low, and so this is another additional feature of the Casagrande chart. With soils with the geological stratum, they fall approximately parallel, what you can see, the parallel to the A line. So, here basically the location of the common clay minerals in Casagrande's plasticity chart is shown. So, here what has happened is that this is the A line and this is U line which is indicated. So, all the three common clay minerals, which are nothing but kaolinite, illite and mantamonite, mostly kaolinite based soils, they actually fall below A line. What you can see is that is the general classification which is actually given after the holes and coax, is that this one, and illites, they fall somewhere here, and here in this zone there is a possibility that here it actually right below U line, it is actually possessing very high plasticity index and liquid limits. The mantamonite based mineral soils will actually fall here. So, if you look into this, the kaolinite based soils, theoretically they actually fall below A line, illites somewhere here, and then mantamonite based minerals say somewhere here. And here in this particular slide, Atterberg limits ranges for the subgraded subgroups A4, A5, A6 and A7 are shown here. So, here what has happened is that the U line and A lines are superimposed, the data which are actually shown. So, it can be seen is that A4, A5, A75, they are actually falling below A line, and to obtain the ranges of liquid limit and plasticity index for groups A4 to A7, and high organic soils, peats and muck groups are actually placed in. So, the ASTO groups are actually superimposed on the plasticity chart. So, it indicates that here above A line, so this is soil which is actually having medium plasticity, and here which is soil which is actually having high plasticity, that is not addressed in ASTO classification system. So, PT type of soils which are actually indicated as A8. So, in the example 4, for a soil specimen given passing 2 mm sieve, let us say that 100%, and passing 0.425 mm sieve is 85%, and passing 200 mm sieve is say 38%, liquid limit is 20% and plasticity index is 12%. So we need to classify the soil by the unified classification system. So here based on the data which is actually given and with the whatever we have discussed, since the more than 12% passing is number 200 sieve is SM or SC, the plasticity index is 7, so the soil classification can be worked out as SC. So in this particular lecture, what we try to understood is that we have tried to look into the significance of the Atterberg limits, what are the requirement of the users of the Atterberg limits and the limitations of the Atterberg limits, and how we can actually classify the soil based on the activity, and also how to classify the soil with available data with grain size distribution particularly and grain size distribution of different types of soils and Atterberg limit test data. So in this lecture we have discussed about two methods, that is ASTO classification system for soil classification system, which is actually widely adopted for highway construction, and unified soil classification system, which is used for the universally. But however, as discussed earlier, this particular grouping indicates the particular characteristics, but this should not be used as a basis for based on this the further investigations are required to be carried out.